Good afternoon, everyone. My name's Brendan, and I'm here today to talk to you about an element of my day job which involves the simulation of complex nuclear systems. So in the United Kingdom, we have a large range of legacy sites, and some of these date back to the 1950s and 60s. Now, a lot of these sites are reaching the end of their operational lifetime, and they'll have to be cleaned out before they can ultimately be decommissioned. We also have a wide range of facilities which are being repurposed. So they were originally designed for one operation, and we are using them for something else. So this presents us with a range of scenarios where we have complex nuclear systems which are being used for something which they weren't originally designed to do. Now, in order to do this safely, efficiently, and in a cost-effective manner, we need to have a very good understanding of how they work, which then enables us to predict how they will operate if we change their operational conditions. So, in the nuclear sector, we have a fairly unique challenge, and it's largely to do with the nature of the materials that we work with. Now, all of these nuclear facilities are very heavily shielded, access is limited, and the materials that they contain are very often hazardous. Now, this makes it very difficult to take out any samples for analysis or to make any direct observations within the actual active plant. So, there's a special place in the nuclear sector, therefore, for numerical modelling. Now, I'll begin with a very simple example of numerical model, and under Andrew's advice, there's no equations, so stay tuned. Now, I'll begin with something very simple that's very intuitive to everybody, and that's the simple projectile problem. So this is the kind of thing that we do in sort of high level, high school maths or physics class, but it illustrates the main concepts that I want to discuss today. Now, what we have here is a projectile. We're projecting at the known velocity, and what we want to try and do is work out how far this ball will travel. So it's the projectile's range. Now, with any modelling exercise, the first thing we do is we assess the system. We try and determine the key physical processes that need to be represented in a mathematical model. Now, in this case, we'll start off simple. So there's one force, gravity, and we know the initial velocity of the projectile. So what we can do is, assessing the physics, we can extract the key physical phenomena. We represent these mathematically with a series of equations, and we solve these equations using a computer. Now, if we did this in this case, we know what goes up must come down. It's quite an easy problem to solve. We know the transit time of the ball, and then we can work out its range. So we get this nice parabolic arc, which is familiar to everyone. Now, if we went and tested this, if we went out into the playing field and threw a tennis ball, we'd almost certainly find, even with these initial conditions, that we'd measure something that's less than we predicted in our model. And that's because the original model is deficient. We haven't included the full spectrum of physics that we need to capture the behaviour for the system. So, what we might choose to do is we'll enhance the model. We'll include some additional physical effects. So in this case, we can include spin, which induces a lift onto the ball. We can also include drag, so the effective air resistance. This gives us a new series of equations that we can solve, and then once we solve these, we find that we're a lot closer to what we measured in reality. Now, this is obviously a step change. It's an improvement in what we had before. Now, we can carry on this path. We can go down, we can continue to add new physical phenomena to make this more and more accurate. So we can include things like the Coriolis force of the Earth, the compressibility effects if the ball is travelling very quickly, the variation of gravitational field strength with altitude above the Earth. So we can do this, and each step that we take will nudge these two curves closer and closer together. But what we find is it's giving us more and more work to do. So ultimately, we find there's a balancing act. We can drill down into the detail, but each of these little effects doesn't really contribute much to the big picture. So in industry, what we do is we assess the system, and we only capture the key physical phenomena that really affect the end result. We ignore all these small effects. Now, there's a balancing act, because if we include all the detail, the calculations become very, very complex, very expensive, very time-consuming, but they don't really give you much difference in your final answer. So what this means is we choose practical solutions, and essentially they're all wrong. And they're wrong because we haven't included all the physics, but they're still useful, and that's the key thing. So what we're doing here is we're providing an approximation of how this system will behave given a set of initial conditions. And that's the important thing here. We don't need all the physics to do that. What we're trying to do is to provide value, to provide a useful approximation, and that doesn't need the full resolution of all these physical processes. Now, what happens if we get it wrong? Well, the results can range from being expensive to being dangerous, and a good example of this is the Millennium Bridge. So this was commissioned in the year 2000 to mark the turn of the century in the new millennium. So it was opened in early 2000 and it was closed shortly afterwards, and the reason being that the bridge oscillated quite widely while people were walking on it. Now, the reason for this was the way that the bridge had been designed. The natural frequency of the bridge is quite similar to the pace at which people walk. Also, the structural engineers, when they did the models, they didn't include the lateral forces that humans apply to the bridge as they walk. And that's what allows us to stand upright. Now, the logic behind this decision was that when you have lots of people walking in a random manner, the forces all cancel out. But as any mathematician will tell you, if you have lots of people all behaving in a random way, occasionally patterns form. In this particular instance, that meant the bridge oscillated. That then changed the way that people walked on it, and it made the oscillations bigger. It was a sustained oscillation. So the construction cost for this bridge was £18 million. As a result of this error in the modelling, an additional £5 million needed to be spent to rectify, to damp down these oscillations. So it wasn't dangerous, no one was harmed, but it was very expensive. And if the modelling had been done properly, then obviously this cost wouldn't have been incurred. So in the nuclear sector, we obviously can't afford to make mistakes. Everything has to be safe, everything has to be reliable. So how do we make sure we get it right? Well, the broad range modelling that we do, we tend to use very well-established, robust, reliable methods. So these are used throughout the process industries, and the nuclear sector is no exception to these. So in the majority of cases, we're using very well-established models, well-established software, and we have a lot of confidence that these give us the right results. Now, there are a range of problems which are unique to the nuclear sector, and for which there are no well-established techniques for resolving them. So this is where UKNNL calls upon its world-class experimental facilities and our collaborative links with some of the best universities in the world to do the research that's needed, the fundamental science that's needed to try and get a model that we can use to provide value to plant. So a good example of this is some work that we've done in support of the highly active evaporators from the Sellafield site. So what we have here on the left-hand side, this is a computational fluid dynamics model. Now what this does is it simulates the fluid flow and the heat transfer processes that work within a HAL evaporator. On the right-hand side, we have an experimental rig which was commissioned and is in use at Heriot-Watt University up in Scotland. Now, the aim here is to do the fundamental science, to understand this very complex behaviour, but then to link it with a real-world experiment. So what we're trying to do is we can come up with a model, but then we test it against reality. When the model works, we can scale it up and we can represent the full plant. This can provide tremendous benefits to our customers. Another good example is of a pulse jet mixer. So this is an experiment that was undertaken at Workington. So these pulse jet mixers are used across the nuclear sector. They're very reliable, and their purpose is to agitate sludge and stop it from forming hotspots. So on the right side, this is a model. It's using a technique called smooth particle hydrodynamics. And this is an example of what Andrew mentioned earlier of taking the leading edge research that's been done at universities and bringing that into industry where we can provide value to our customers. So I'll end briefly with a short case study. So this was some work that we did just a few months back, and this is a fuel store. So this has been repurposed, and the customer's query here is, can I load in a new set of fuel? This is quite exotic fuel from a range of reactors. And what we wanted to know was, is it safe? How will it operate? And what happens if the ventilation fails? So in this store, the green box at the front is a ventilation inlet. So there's a big fan that blows air into the facility, and then that cools the fuel that's stored inside. So the air goes into the green box, along the yellow channels, and up these cylindrical tubes. Each tube contains a fuel assembly. And what we want to do is assess the system to determine whether it's going to be safe. So once when the air goes past the fuel, it extracts some of the heat, and the heat's then expelled from the system through the red squares at the front and back. So this is a relatively straightforward problem. What we have is flow going in, the flow goes past some of these tubes. We can break it down to establish the key physics, as I mentioned before. In this case, there are two driving forces. There's one is the ventilation itself, providing forced flow, and there's one that's the buoyancy-driven flow, which is influenced by the temperature within the store. So all of these physical processes are well understood, well established, and we have a range of modelling tools available to capture all of these. When we run the simulations, what we found is these results here. So basically, the store behaves, this is for normal operations, the ventilation fully active. So flow enters through the inlet, passes through all the outlets, passes through all the assembly ports, and cools the fuel. Now, the important thing here is that the majority of the airflow goes to the extreme outside of the store, which is great for the customer because they know straight away to load the heaviest or the highly active fuel rods in that part of the store where they benefit most from the convective cooling. If we crank down the inlet flow rate, so what we're doing here is we're simulating a loss of cooling, so if there's a power cut on site or there's some kind of accident on site, what we find is really interesting, and this demonstrates the power of the modelling because we can't simulate this using hand calculations or experiments. It's too complex, it's too big. But what the modelling shows us is that if you turn off the ventilation or crank it right down so there's hardly any flow entering the store, the buoyancy forces are enough to suck in air from outside. So what that means is even if you have a loss of cooling, this store remains cool and it remains safe. So that's great for our customer. So ultimately, we can pass on a temperature map of this facility under a series of different operating conditions that basically tells our customer where they can place the fuel to make sure that the store will run safely and efficiently. So, just to briefly summarise, NNL has an extensive modelling capability, and this covers all aspects of the fuel cycle, a range of different length scales and temporal scales. This tends to be based upon a series of very well-established, tried and tested modelling techniques, which are used across all the process industries. Where these models are insufficient, we have the capabilities to do the fundamental research that's required to come up with new models and test them against experimental results. Ultimately, what we're trying to do is to provide useful information to plant operators to make sure that their facilities are being run in a safe, efficient and cost-effective manner. At the heart of all of this is the understanding that whilst all models are wrong, some models are useful. And in NNL, we endeavour to make sure that all of our models are useful. Ladies and gentlemen, thank you very much.